right?
Yep.
Yeah. And we met because of I don't know, over the years he kind of lost track about what we were doing here and the fact that we've really been building up economic geology. That the department pushed, that's when Hannah came on board, but we've been doing this. And in part because of where we live. I mean, in our school, we really take seriously this idea. I'm just keeping my chair.
We were in the wrong room.
Good to see you.
That's why I waited.
Oh, wait, how are you? Good to see you.
Young people can figure it out.
I mean, I sat in the wrong room.
Anyway, I think I've probably stalled it up. Rich is currently the administrator, and he'll probably fix this, but in charge of mining, minerals, energy, so resources in Nevada, and has been long connected with the department. Supports, comes back about every year or so and gives a talk, and has helped with students and connections in Nevada. So we're really glad to have this special talk. But the reason he's here for, you haven't heard, for this trip, is he was also the distinguished alumni for the College of Natural Sciences. Hence the dean and being here. Which I believe is our. It is. I believe it's the first time a alumni of geological and environmental sciences. Maybe you know, Howard, but I think it's the first time we've gotten.
I think it's the first.
Yeah, and very well deserved. So without further ado, Rich Perry.
Thanks. It's good to be back, and I was feeling very unpressured until two of my former professors came in here. Now they'll be grading me here in the back of the room. So I have a presentation here for you today, which I think you'll find interesting, and I'd like it to be kind of a two-way dialogue. Stop me as we go along here. It was actually put together by another Chico State grad who works for me at the Division of Minerals, Lucia Patterson, who graduated 10 or 11 years ago. And what we kind of schemed up here, which I hope is kind of a unique way to look at this. Usually you have a presentation on geology or mineral deposits or tectonics. What we've got here is one that tries to wrap in the tectonics of the state of Nevada, what kind of rocks were formed during that period, how they were structurally prepared, and what type of mineral deposits are found in a geologic time scale. So we're going to start here in the Precambrian and kind of work our way through it. So stop me if something doesn't make sense, or correct me if you hear something wrong, because I'm a little rusty on some of this stuff myself. So I'm going to start here with this slide here, of the state of Nevada, which is this geologic map that you see right here, and just talk a little bit about, the state itself and the 2 billion years of tectonic history that we have here. The oldest rocks of which are up in the East Humboldt Range. And if you ever get out that way in the East Humboldt Range, there's this really beautiful lake in the Forest Service area called Island Lake. And right up above that, if you walk around to it, you'll get right into that section, which is a really interesting thing to do, to walk through the Precambrian. So some terminology here on ore deposits as we go through this. Carlin-type deposits, which are sediment-hosted disseminated gold deposits, and that's what Nevada's best known for geologically. Stratiform deposits, where the deposit is formed along with the stratigraphy as a replacement deposit or something similar to that. A VMS, or volcanogenic massive sulfide deposit, which forms from black smokers in the ocean. We've got some little models we'll go through here, but I wanted to introduce these. For those of you, how many of you had economic geology? Good, so good portion. Okay, good. Porphyry deposits, which are igneous intrusives, and where metals concentrate at the very top of them. Skarn deposits, where you have igneous bodies up against carbonates that dump these loads of metals along the margins of those. And then epithermal deposits, which are those that form mainly in volcanic terrains from solutions coming up, and those are the ones that things like the Comstock lode are made of. So those are the kind of the 6 type of deposits, and we'll kind of work our way through here. So let's go way back into the Precambrian, when the supercontinent Rodinia, was out there, and you can see here's where Nevada was, right there, along this margin right here. This is even before Vic Fisher and Howard Stensrud were teaching here. This is an old supercontinent, okay? And the red dots there are A-type granites. But okay, so you usually see tectonic books that show that, and this is borrowed from one. So now we're going to move into the late Paleoproterozoic, so the later Precambrian, right? Post-Archean, and you can see again where Nevada was then. So I'm going to have some of these slides in here that we put in. Middle Neoproterozoic, so we're still in the Precambrian there, but where Nevada was on the edge of a continent. And now I'm going to give you a color key, because the next group of slides has 3 colors. The blue is an explanation of the rock and structural preparation for mineralization that occurred during that geologic time in history. The black is a geological description, and the red are the mineral deposits that formed during that period. Make sense? Okay? And by the way, I will have everything that I give presentations on will go on the Division of Minerals website. So if you want this presentation in a week, go to www.minerals.mb.gov and it'll be there in recent presentations. Okay? So here's the first of those slides, and we're going to start in the we're now in the Cambrian and Devonian, so we're in the early Paleozoic, and we're looking at a cross section of Nevada here. And you can see that at that time tectonically there was an east-facing arc out there that was approaching western North America, and during that time there was a lot of carbonates that were formed. Here's where California is in all these slides right here, right? Here's where Nevada is in the cross-section, Utah, and then on over to Colorado. And you can see that Nevada was mainly a carbonate shelf, right? So those are the limestones and dolomites and so forth that were formed then, that, like the Roberts Mountain Formation, a lot of eastern Nevada are composed of, and are actually the host rocks for a lot of the mineral deposits. So there's actually some of these mines. So here's the first slide of an actual mine, right? And that is down here in Clark County. There's a limestone and a Devonian limestone, the Sultan Formation, and a little bit later Mississippian Dolomite that are mined. You can kind of see the bedding of those right here, and those are mined by a company called Lhoist. Lhoist is a major lime producer. They have mines in Nevada, Arizona, and all over the world, and they produce chemical lime for various purposes, and that's a chemical lime plant right there. So mining limestone and mining dolomite. These 3 kilns actually are calcining limestone. That one is the dolomitic calciner there. And that final product is used, chemical lime is used from everything from pickling asphalt to scrubbing systems, making concrete and so forth. And as you can imagine, that's a pretty big business down there, wherever you're constructing with lime plants. I remember there was one of these plants to the north here, north of Reading. It was mining the McLeod limestone, and the conveyor went underneath the highway. Is that still running?
Yeah.
Is it? Good. Okay. Mining that. And we'll actually get to that, because we're going to talk about the McLeod here and where it fits in later. So let's move forward into the Devonian and early Mississippian. And you can see here in Nevada, we've got the arc collides with the western North American passive margins here. So these carbonates that are here are there, and they're starting to collide on a plate boundary there. And during that time, the barite deposits that are mined out in central Nevada that Russell's working on were formed, right?
Yes.
Yep. So that's what it looked like at that point in time. And the antler orogeny is the term for that tectonic event. The antler was the first major tectonic event, and it thrust siliciclastic rocks that were out in the ocean here over the carbonate rocks. And that's significant from the standpoint of the mineral deposits in Nevada too, because that siliciclastic allochthon that went over the carbonates basically formed a cap or a seal on top of them. So later, when the mineral deposits came through, they were trapped there and helped form them. So here's here's kind of a little cartoon of what that looked like. So you're out here in the ocean, and you've got a black smoker plume, right? Which, you guys all heard of a black smoker? Kind of in the middle, mid-ocean ridges, and the minerals come out of it, and they form around it. And then the barite deposits, though, formed right at the oxic and anoxic boundary. So the oxygen and the non-oxygen boundary there as really replacements of existing carbonates, I would say, right?
We'll talk later.
Okay, yes. Russell's working on it.
It's a good start.
That's a good start, all right. We have an expert. So let's move into the Mississippian here. And you can see that part of Nevada is out of water. That's the Antler Highland is what it's called. And the Antler Orogenic Belt, and it's got on the inside of the Antler Highland, you have a shallow inland sea, which is close to the Utah boundary. And as the Antler Highland was eroding, those sediments and so forth going into that shallow sea were shales and organic materials, and they're believed to be the source of most of the oil deposits that are found in eastern Nevada. Okay. So, a quick slide on oil in Nevada. We don't really have much. It's almost all out in the eastern part of the state in the carbonate hosted material, and not in the accreted terrains that come through, but there has been some production of that. These are actually oil leases on federal ground in Nevada. We track those. Our peak oil production was about 1990 at 4 million barrels, and we produce less than 1 million barrels at this point in time. The very reason that Nevada is not a great oil state is the reason why it's a great geothermal state, because it has a high heat flux. There was oil out there millions of years ago, but with that high heat flux that came through, it cooked it all. And that's where the organic material in many of these ore deposits actually was formed.
Rich, I thought the Big Smoky Valley, wasn't that named because of this kind of constant hydrocarbon haze from the methane? That's why I guess I'd heard that.
I don't think, I think it's just the fog, that's right here.
Yeah.
Right, but there's actually no oil production there. The oil production is all
methane.
Methane, huh?
Yeah.
You may be right. I don't know. Whenever I go through it in the wintertime, it seems like it's in a fog.
Yeah.
Big Smoky Valley. Okay. And there's no oil well in Railroad Valley. So I think we had 120 wells active last year. And not any real exploration for the last few years. About 5 years ago, there was some.
So, are they still trucking all that oil to Salt Lake City?
No, there's a refinery in Railroad Valley. It has
Where
been
is
for
it?
40 years. Yeah, the Forland Refinery. No, they're trucking oil from Utah into Nevada to keep the refinery filled. And that refinery is a single distillation tower refinery. And it produces asphaltic products that are used in roads, basically, and some diesel. It's a heavy asphaltic oil. The exploration that was done back 5 years ago by Noble Energy looked at some Oligocene age shales around the Elko Formation, and they found those at depth, but by the time they were ready to start drilling in earnest, the price of oil tanked. So they pulled out and plugged their wells that they had drilled. So we're in the late Mississippian here. Again, we've got a highland going across the state, and we've got this shallow sea that exists behind that highland. And we had a directional change in the subduction zone created by an extensional back-arc basin, and a formation called the Hvala Formation. It's called the Hvala Basin. Was forming out here in the ocean. The Hvala is chert greenstone argillite. I actually did my thesis in much of it, and it was formed during this period, and then it was thrust onto the continent slightly after that. But let's go to another cartoon here. Again, a cross section through a black smoker, trying to explain a little bit of why the Hvala has some volcanogenic massive sulfide type deposits in it, because there's been a number of them that have been found and mined over time. So the Hvala has those greenstones, and it had black smokers during the time it was being formed, so it saw some relatively high-grade copper deposits that were formed. Unfortunately, as it was thrust onto the continent, they got sliced up and they're hard to find. So they're literally in pods out there. Who knows what a white smoker is? No? No guess? So I'd ask Lucia this. Black smokers are low pH, white smokers are high pH. And you tend to get more zinc type mineralization out of white smokers. So the late Pennsylvanian here, again, you can see the pattern there, and during this time you're starting to see compressional forces of the Humboldt orogeny, which would exist throughout the Mesozoic, and some exotic terrains were accreted onto the continent. These events resulted in the inversion, the reactivation of some of the Paleozoic basement faults right here, which would later serve as conduits for the depositional sites for the porphyry coppers and Carlin type deposits. So again, we're starting, as we go through, we're talking about sort of the structural preparation of these rocks that will later, in the Tertiary, form many of the precious metal deposits that are out there. The Sonoma orogeny, which is a component there of the Humboldt, was Permian, early Triassic, and that formed the Golconda Lacna. So the Hvala was thrust onto the continent over here, and imbricated, and if you've been out in Nevada very much, really that section or that terrain is between Winnemucca and Carlin, right? As you go across Golconda Sound. Make sense? Okay. How many of you have driven I-80 across Nevada? Yeah. Okay. Good. It's a great cross section of geology. You can see all this, like the antler. If you want to see the Roberts Mountain thrust, right before you go into the Carlin Tunnel, you just look off to the left, and there it sits in a giant outcrop 1,000 feet high, and you can see the siliciclastic rocks over the carbonates right there. But don't look too long because the tunnel is kind of narrow. So,
Rich,
yes.
Question, along the thrust, you mentioned it was a cap, but are there a lot of fluids moving along that thrust? Can we track lines along the Roberts Mountain thrust?
Yes, and I have a map of that. But the fluids weren't then, right? That's just the structural prepreparation. They come later.
It's the pathway.
Yep. And that, like in the Cambrian, one of the first slides, noted a lot of west-northwest trending faults that were formed during that period when the carbonates were set. And that's actually the ore controlling structure for most of those deposits came from back in the Cambrian, early Paleozoic. So sea level regression and arid environment and tectonics during this period created supertidal salt flats, or sabkas, right? And partially restricted marine basin environments, which would facilitate some of the older gypsum deposits that we've mined in the States. So things got dried up behind that back arc basin over here. And you can see too, here this shows up, right? The McLeod Arc, piece of geology over here just to the north. The McLeod limestone is Permian age. I did my senior thesis in the McLeod, so kind of close to me. Okay, let's go on and look. Now we're in the Triassic, and we're starting to see the pattern of all of these accreted terrains that are subducting into the North American continent over here start to stack on each other. The late Triassic, most of the mountains that subsided from the Sonoma orogeny were being covered by upper Triassic marine sediments. In southern Nevada, the silt, gravel, and mud of, you may recognize these if you've ever been to down in Arizona, because they exist down there around the Grand Canyon. These formations here also exist down in southern Nevada, where deposit is as the land dried up and ocean progresses. So the Triassic really was, to me, the age of sandstones, right? A lot of sandstones were formed during that period in southern Nevada from erosion of the Sonoma rocks. that were deposited earlier. So here's an example of these, and a rather unique one that I really enjoy going to. We take the teachers every year, the teachers workshop that we do in Southern Nevada, to this Las Vegas rock, which mines Aztec sandstone in a quarry called the Rainbow Quarry south of Las Vegas. And the Aztec is a very colorful, tan and red sandstone that just happens to be pretty consistent in all three directions as far as its compressive strength. It has very few fractures in it, so you can use it literally to make furniture. That is a chair, okay? And that's actually built, they put a slab of sandstone in there, and it will sit there and it will actually carve it. It's not glued together, it's literally carved. They have equipment that will do that. This is a machine here. They have one of these that sits there. You put a big slab of sandstone in, and there's a saw that goes back and forth, and it makes the sandstone that's used for tables at bars. You can see them in some of the casinos down in Las Vegas. The sandstone is used a lot down there for decorative stuff, and it's really beautiful product. And that's Aztec sandstone from the Jurassic. Okay. The other place down there is Simplet Silica, which is near Overton, and again, that's I believe that's Aztec also, but it's not all cemented together. It's rather loose in this deposit here, and that's mined for a number of different products by Simplot to make fiberglass, grout, cement, concrete, glass, and I can almost guarantee you if you've tipped many beer bottles, you have glass that came from that quarry right there. That it was made from glass from Overton. Okay. Sometime during the Jurassic, the Farallon Plate. Now we've got this one out here on the coast of the North American continent. The Farallon Plate reached depths where pressure and temperatures increased to the point where water vapor, it got hot, right? And the oceanic rocks induced melting, and we started to see these intrusive rocks formed out here. So the reds are the granites and the granitoid type rocks that are coming up. That was the period at which a lot of the stocks and batholiths out in Nevada were formed, and a lot of the dikes too. And many of those used old basement faults to come up, the preferred pathways. And the intrusions were responsible for the porphyry and molybdenum deposits that are mined in Nevada, because that's the nature of those types of deposits. Porphyry deposits of copper, of which Nevada's had a number of different ones mined over the years, and molybdenum. So stresses generated from those rocks created fracture systems in which sills and dikes created aquetards and would later control some of the flow of the Carlo-type deposit fluids. And there was also some period there where some of the skarn-type deposits, this is when some of the skarn-type deposits were formed in the state. But you can see the cross-section here, pretty complex. We're still colliding into North America, so we're accreting more of Nevada. Here's an example of one of those deposits. This one actually is, I'm going to show it to you. This is what it looked like about a month ago. This is outside of Yarrington. And underneath this is a very large copper magnetite deposit that was actually found in the late 50s by U.S. Steel. They've known it from geophysical evidence, and they had drilled it years ago. And it has come to the point where it is now economic. It's about 2% copper. It's a picture of a sample that I took out there. This is chalcopyrite, a polished piece of rock. This is the head frame that was built over it. So they have built a head frame, and they have sunk shaft 2,200 feet deep, and they have now done the workings from the bottom of the shaft, the development workings, to get it set to where they can start mining the deposit. They actually have some of the ore at the surface, and what they're building here is the concentrator. They have a 5,000 ton a day concentrator. This is a flotation concentrate type thing. So that'll be the third operating copper mine in the state, and that's good news. That's $90,000 a year jobs down in Yarrington, which are well received down there by that community. So, and during that time also, the Rochester rhyolite, which is out in Pershing County, was mineralized with one of the biggest disseminated silver deposits in the state. And I notice I have one too many fives here, so that's 54,000. So that's actually our one primary silver mine in the state. is out there at Rochester. And that mine's been in production for about 30 years and employs about 500 people. And you can see here, it's a surface truck and shovel operation, heap leach.
Rich,
Yeah.
what's a typical ore grade on silver for?
About 2 ounces per ton. And the gold grade is like 0.1. So if you do the math here, 5 million ounces in 2018 and 54,000 ounces of gold, you actually come out with a little more value in the silver than you do gold. Precious, in most of these deposits like that, gold and silver are found together. They're zonally connected in most, not all, but in most of the deposits. Rochester just happens to be a big, bulk mineable, disseminated silver deposit. Yep. And they hire
That's like
interns and geologists every year, so they're a good one to go to. That's Core Corporation. It's called Core Rochester. Core is a mainly silver mining company that's headquartered out of, I think it's Chicago now. It used to be in Idaho, but they have 4 or 5 mines throughout North America, and I think one in Mexico, a couple in Alaska. Any other questions? No? Good. Okay. Now, where does civil engineering come into this, right? Let's talk about that just for a moment, since you guys raise your hand, because I love it, because I work with many civil engineers in mining over the years. The leach pads, the foundations, the constructions of the mills, and all of those things, all required civil engineers to design and stamp and construct them. So there's civil engineers, mechanical engineers, mining engineers, geological engineers. There's a symphony of people involved in producing a mine. So now we're in the early Jurassic, and we see some more terrains coming and hitting Nevada out here, right? And starting to get closer to what it looks like. Now we're in the late Jurassic, and we're out of the water. California is still not out of the water, but you can kind of see the Central Valley here, right? It's coming. So during the Cretaceous, Nevada was located in the hinterland, and the event was the Sevier orogeny. This event added to the complexity, and because it was continuing to collide, and Nevada actually, the geology got shrunk. 20. They estimate 22 to 45 miles. So all of that thrusting over the top and squeezing, and because of the subduction and the forces that were coming up there, caused the rocks to fold and fault, And at that point then, I should note too, because we're now talking about California, right? That's when the Franciscan assemblage was accumulated. So it's also of similar origin. You guys familiar with the Franciscan Formation, right? The Coast Range, right? Inverkit, Trustee. Used to be one of my favorite places to go with there because it was such an interesting piece of geology. Okay, and during the late Cretaceous, that subduction angle began to flatten. Okay, right here, the angle wasn't so deep anymore, which caused a large plateau to form on top here, which is referred to by the structural geologist as the Nevada Plano. The uplifted area created a drainage basin on both sides. The sediments were flowing into Utah and back out into California. Now, significant for here, right? Rivers in this drainage basin system would later cut into the Sierra Nevada granite, and its Mesozoic lode gold ore deposits, creating the large placer deposits in the Sierra foothills. Discovery of these in 1849 resulted in this big migration that we had across the country. And when that was subsiding, and in 1859, people started wandering back in Nevada and found Comstock lode. Same bunch of people reminding over here. So here's what it looks like. Here's those accreted terrains, or those exotic terrains. So here's the Cambrian Silurian section over here, the Roberts Mountain thrust on top of it, and then the later Sonoma orogeny and the Golconda thrust sheets sitting on top of that. And then here are some of the the smaller accreted terrains that showed from some of those later tectonic events that thrust different terrains up onto Nevada to what we know as today. So kind of a good tectonic map of the state there, of different way of looking at it, I would say. Huh? Okay, so late Cretaceous here, looks like we've gone the other way here, and we have some tectonically quiet period, and what's called by the structural geologists a flat slab subduction. So that's what you see here. I'm not so familiar with that period. So the Paleocene brings us into the Tertiary, right? So Oligocene, the subduction stopped, and the Farallon plate, backwards. The angle of the Farallon plate steeped, resulting in the reintroduction of the hot mantle at the base of the North American lithosphere. Volcanic activity was associated with areas of early extinction. Of similar or equal age to this volcanic activity are the Carlin-type deposits, whose hydrothermal fluids were derived from both the mantle and the metamorphic rocks. These fluids migrated through the crust utilizing pre-activated pre-Eocene structures and carbonates to facilitate that process. So here's when we're starting to see the gold deposits, solutions for the gold deposits coming up along activated, reactivated faults and form in those carbonates. And here's a picture of those. This is the one I was referring to here, of the Carlin-type deposits. So this is the 4 areas where there are a majority of production that all come from similar age rocks out there, the Cambrian, Ordovician, and Silurian carbonates. And those areas are the Carlin Trend, which is right here. There's any number of mines up there. And the Carlin Trend's produced about 90 million ounces of gold today in its lifetime, since it started mining in the early mid-60s. And then the Cortez Trend, which is a bit newer, which is right down here. It's called the Battle Mountain Eureka Trend, but that's Cortez right in here. Getchell, which is over here, in the Getchell Mountains in Humboldt County, and Jarrett Canyon, which is north of Elko here. As you see, those are the locuses of the mining operations where the geology was run.
I don't understand your use of the term endowment in this context. Like, what's
The endowment is a term of how much gold was endowed into the rocks, literally.
So the theoretical production.
Right. Right. Well, it's the theoretical total amount. It's not the production. Production's still going on, but it was endowed with this large hydrothermal system that deposited all these precious metals in that environment that began with its structural preparation in the carbonates back in the Cambrian. So that was kind of the intent, is to sort of show that here of how long that was, how much complex geology there was before it actually had those gold-bearing solutions going through it to form a deposit.
Can you give an idea of how much rock has to be produced in order to get an ounce of gold
Sure.
from a carbon deposit?
Sure.
And also, these are some of the richest gold mines in the North America, or?
Well, I mean, rich
That's
as in grade, you know, I think that's why this term endowment, you hear it more often, because it sort of encompasses everything. It's how much volume of ore that was formed. Because, you know, you have low grade ores and you have high grade ores, right? And when you ask the question, how much rock has to be moved? Well, you know, when I first started work out there in the mid-80s, everything was open pit mining, surface, right? And there was high and low grades in those. It was all above the water table, so it was all oxide, and you could process it through oxide mills and oxide leaches, and those were the great days. And then as mining progressed, they mined all the oxide surface stuff out. About 1993 or 4, I remember, I was up at Jerry Canyon, and the first underground mine started, because we hadn't had any underground mining there for years. We'd sort of lost that as an art, not just in Nevada, but in this country. And we literally, I was working for Independence Mining then, we had to go find underground miners so that we could learn how to underground mining it. Underground mining chases generally higher grade ore. So, I mean, I remember when I was at Newmont, we mined the Deep Star deposit. It was 2 million ounces of 1 ounce per ton grade.
2 million to
It was a million, it was 2 million ounces total that we recovered, and the grade was 1 ounce per ton. That's high grade ore, okay? And that was at the bottom of the Post Betsy pit over about a 3-year period. So there's good high grade ore, and it was black, sooty stuff that had to go into a roaster in order to be combusted so you could leach it. So it's refractory ore. You know, you compare and contrast that with some of the open pits that might be mining 0.1, 0.2 ounce per ton, where you have to move 100 tons of rock to get an ounce a ton. It just depends on the economics. You have to do the economics on all of it. You know, you gotta say, is this economic or is it not? You know, every year when the mine planners go through with their mine planning for the following year, you know, the corporate office says, plan on $1,200 an ounce gold. It's always lower than it actually is, because they have to have a return on it. Design your pits and your underground mines to this grade. And then they start crunching through, take the drill hole data, build models, cross sections. It's, you know, we used to have to do it by hand with planimeters, but now there's programs that do that have geostatistical software attached to them, so that you get much higher percentages of what you're actually going to mine when you do it, and you do your mine to mill reconciliation. So it just depends on how many tons, right? At this point in time, as of last year, between 30 and 40% of the gold produced in Nevada is from underground mines. It's increasingly going underground for several reasons. Number one, it's a lot easier to permit an underground mine. We've become good at actually doing it. We have people that know how to do it. We've trained, you know, Americans, and there's an underground mining skill out there. There's thousands of guys that work in you know, go down underneath the ground, and it's not like the ugly looking stuff that you see in coal. They're like little cities with maintenance shops and lunchrooms, but they're all underground, right? And they're automated equipment. Some of the equipment is autogenous equipment for certain of the things that are dangerous. There's autogenous loaders under, there's autogenous trucks that run off of leaky feeders that are projecting radar in underground workings, because GPS doesn't work. 5G is not going to work underground, right? You have to build your own nodes down there to do that. But it's pretty high tech. This isn't a low tech industry at all. I mean, everybody talks about tech. Well, tech is great, but tech is there to make you know, industries that produce a product more efficient, right? That gets lost sometimes, I think, in people. You know, so that tech that's always being developed, the GPS. I mean, the D11 dozers in the pit in Gold Quarry when I left, you know, 12 years ago, had GPS control on them, and the engineers would plug in what they wanted that dozer to grade to. And there was a guy on it that could see a screen, and he could tell as he went down and graded a road in the pit if he was on grade or not. You know, that's the level that it has come to. Yes?
And that relates to my next question, is disseminated gold deposits, how much of a geologic framework do you need once you've started a disseminated gold mine versus engineering in order to get this stuff out? Because you're just going for bulk rock, or not, or not.
You're not.
Okay.
You're not, and I can say that because I have mined disseminated gold deposits and I have mined porphyry copper deposits.
Yeah, okay.
You know, I started up a porphyry copper mine in the Republic of Indonesia on the island of Sumbawa for Newmont in 1999. And we drilled the entire multi-billion ounce deposit out with 120 core holes. Because that's all it took.
Wow.
The deposit was so homogeneous.
Yeah.
You know, and porphyry copper deposits are that way. Gold deposits are very stratigraphically and structurally controlled and very geology intensive. most mines, like an underground mine, after they've shot around, the first person that comes in, you know, to muck it, right, to get it out of there, and then the geologist is in the face immediately looking at, where is this going? Is it going this way? Is it going that way? Do I need to put a drill rig here? Especially the bonanza deposits, I know of, like the Midas mine, which is mining 200 tons a day of 1 ounce material in a bonanza gold deposit today. And there's a geologist at the face every shift, because that's, gold is so different. It's just not homogeneous. It's very structurally and stratigraphically controlled, and it takes a lot of geologic horsepower to keep you on track, grade control. Russell?
Just thinking the Carlin trend of for the going underground like a deep star, isn't it also, is it the shape of the pits? I mean, at some point, it's not economic to do the overburden.
That's correct. And you know, when you think of the cross section of an open pit, right? The ore is always at the bottom, pretty much, or in the, you know, in the hanging wall, footwall, or whatever, depending on you're chasing it down. And every time you have to go deeper, you have to lay back the pit, and there's all that waste that you have to lay back, and there hits a point where it's not economic to do that anymore. I remember doing a layback in the gold quarry pit. It was $80 million just to strip to get to the ore, right? It was a big stretch, and that depends on the price of gold, but it gets to a point where you're better off chasing it from the bottom. And the first one of those was in the gold quarry pit. It was called the Chucker Footwall Mine, and it's still there. And I remember we had blocked out in the footwall in the Roberts Mountain 200,000 ounces of like 0.3 ounce per ton material, right? And we said, let's go. And we hired SMD to do a portal and drifted back into it, and then went along the grade or along the strike of the ore. And that was 14 years ago. And that mine's produced, last time I talked to one of the mine geologists, 2 million ounces of gold since then. We started at 200,000. So once you're underground, you just keep finding. You put drills along the workings, and you just start drilling, and you don't have to drill very far to delineate the deposit. That's why gold is so challenging. It just takes a lot of sampling, a lot of drilling, and a lot of geologic horsepower to make them. They just seem to go on and on. You know, there's been, I mean, the gold rush here, I forgot this number, I used to know it. I forgot how many millions of ounces, but this area in itself has produced over 200 million ounces of gold, and that dwarfs the California gold rush. And that's since 1965. Yes?
Are you just drilling into like the base of the mountain, or are you guys drilling like how far down are you guys going?
So it just depends on what your target is,
Okay.
and you're drilling with.
Using like radar to detect and all that?
No, you've done maybe geophysics, you've done your projections of surface geology, you know, and I'm assuming that, you know, that you don't have an underground mine there, because if you had an underground mine, you're probably drilling from underground in a drill bay. But if you're looking for a deposit, you've got some surface expression that the geologists have mapped out. You've probably done some geophysics to look at, you know, magnetic air, the other types of geophysics that I always forget, right? Electro. You look to see if there's sulfides underneath. There's any number of geophysics that will kind of tell you. Probably not seismic, though. You know, seismic is more of an oil thing. And then they say, gee, I think that there's a target down there, and that target is at 775 feet. And I need a sample of that to determine, A, does it have gold? So I'm probably going to go in with a rotary rig first, a reverse circulation rotary rig, which drills cuttings. You know, it's going to bore a hole, and the cuttings are going to blow back up, and you're going to collect that, associate it with the depth, send it in for assay. Now, eventually, if you want to take that to what's called from a resource to a reserve, because there's just like in engineering, when you stamp something, there has to be a geologist or engineer that says this ore reserve calculation is 43-101 compliant. There's rules for ore reserves so that people aren't out there in the stock market pumping things that don't have any standard to them, and there's people that do that. I'm a certified professional geologist. I can do a 43-101 report. but I have to put my stamp on it. And if it's wrong, then I can lose my license,
Right.
you know? But they would go back in with a core rig, okay? So they found it's relatively inexpensive to drill rotary per foot. It's more expensive to drill core, but core gives you a physical sample of the rock. And you know it's not got any contamination from groundwater or something like that, right? Even the oil guys do this now. When they get down into these oil zones, they drill core because they need a sample of the rock that they can calculate the permeability, porosity, and transmissivity of the rock. All of those things need to come out of that.
But does the Security Exchange Commission regulate you when you look at when you assay a mine and say how much it's there? Who regulates the people that say how much gold is endowed?
Okay, so there's a Canadian form of it and there's an American form of it.
Oh.
Yes, there's two different ones. And the 43101 compliant number is a Canadian term, actually. There's different terms under the American, and if you go to the Society of Mining Engineers page, you can pull that up. Because there's papers on, here's the definition of resource and reserve. Proven, probable, possible, right? And all of those have terminologies that are approved under those, so, yeah.
It's pretty significant because that's your investors are looking at that.
That's exactly it, yeah. And all of that kind of came out of, if you remember the Briac scandal about 20 years ago, 15 years ago, when somebody in Indonesia pumped up a lot of things and sold a few $1 billion a share in the stock market and found out that it was just salted. Somebody was putting plaster cuttings in it. Anyway, so let's go to a carbon type deposit. How am I doing? Gotta move along, huh? How many of you guys got classes at 1? Okay, so I gotta move along. So here's what happens then in a carbon type deposit. So we've got these Cambrian, Ordovician, Silurian carbonates down here, and we have a structural fault that was probably northwest northwest trending that actually formed through one of these tectonic events back there. And these hot solutions that come up are moving through there. They're decarbonizing the carbonates. They're replacing it with silica. There's parts of the carbonates that collapse into these collapse breccias, and that at the surface when it's exposed is called a jasperoid. And the ores are forming in that envelope there as these hot solutions come up and react with these carbonates. Okay? Make sense? Yeah, a little cross section out there. So
Actually, just going
Yeah.
back, because this goes back to top, I think part of it is that black line at the top. That's Robert's Mountain's thrust, right? So you've got the seal above it.
Yep.
And that's what's pooling all these fluids
Yep.
underneath.
yeah, they're coming up and they can't get out, so they're spreading out into the structurally prepared, first through the faults, that's your primary one, and then secondarily through the stratigraphy that's been prepared. So now we're in the Oligocene, and we see the Nevada Plana there, and we are forming an environment that is about to form what we know as Nevada today, because what really happens there is the Farallon plate moves north, because it's up by Washington now, right? And it's replaced by a giant strike slip fault here that is now the tectonic boundary of North America, the San Andreas. And during that time, we see a lot of the bonanza type epithermal deposits, which are volcanic terrain, because during that time we had a lot of volcanoes that formed and went up some of these faults. So here's a bonanza type epithermal deposit, right? And this is the Comstock Low. These are in volcanic terrain, and they're a bit different in how they form because they don't have a cap on them. They have the faults that are out there, and they have hot solutions that are coming up from the mantle that are leaching metals below, and they're forming hot springs on the surface here. If you go north of Reno, Steamboat Hot Springs, that's the top of one of these things. There's a lot of hot springs, and those deposits are called sinters, because when it comes to the surface, the silica floods and forms these sinters. The hot solutions go and they alter the volcanic rock around, and there's some alteration types. So tropholytic, silicic, argillic that form there that are good indicators there. Okay. And now we have these hot solutions coming up, and they're under pressure, and as soon as they hit a point where that pressure goes away, it boils, right? And boiling concentrates up the metals that are down there, and that's where the ore is found. And those are typically zoned at the top of the deposits of the precious metals, and towards the bottom you start to run into the base metals, copper, zinc, lead, and those types. Virginia City's one of those. I mean, probably the richest hill on earth when they found it, because Virginia City graded several ounces of gold and hundreds of ounces of silver, and it's bonanza days. It was quite the deposit. So here's one of these that was actually found, and this is the Midas mine, and it was found about late, as I recall, the late '90s, by one of my classmates at Mackey. Ken Snyder was his name, kind of a quiet guy, used to do a lot of exploring. And he was in a Bonanza Gold District. Nobody had really drilled into one of these for many, many years. And that was Midas. It was an epithermal vein system. And it was put into production. Here's the portal of the mine, truck coming out from it. And here's I saved it because it was a Newmont mine for a number of years. I saved a piece of the vein here, which I'll pass around. So this is epithermal vein from the Midas mine. I don't remember what level, but it's quartz after calcite, quartz pseudomorphous after calcite. That's what they call the dog's tooth structure, right? That you can see. And those little gray things are silver selenites that are floating through it. And I don't think you'd see any gold in it, but it probably averaged half an ounce per ton of gold and maybe 20, 30 ounces of silver. So it's pretty high grade ore. Yes?
They're active hydrothermal systems. And what are the dangers or what are the hazards associated with mining these?
Well, this one, as you got deeper, was hotter. And that's very typical in Nevada. As you get deeper, there's a high heat flux in Nevada. We have a shallow crust, so no matter where you go, it's going to get hotter in there. But some of these systems are partially, still active. And you have to use more ventilation. In some of the operations, you actually have to use some refrigeration there, but not to any great extent like South Africa, but blow more air typically and cool it off. Yes?
Can you talk about the fly geyser?
The fly geyser?
Yeah.
I sure can. You've seen a picture of that, huh?
Yeah.
Okay, so that's an interesting one, kind of unrelated, but having worked for water resources, the fly geyser's out by where Burning Man happens, right? Is that where you saw it?
Yeah.
And it's this travertine-looking thing.
I haven't seen it. I just seen a picture and I did a little bit of research on it.
The fly geyser actually is a failed well. Somebody drilled a water well out there and never capped it, and it's been flowing for years of geothermal fluid that comes and pops up.
It's like all different colors.
Yep, and the carbonates, when they hit the surface, become saturated, so it forms travertine. But it is not natural.
Right.
It is a groundwater well that somebody drilled and did not plug.
Cool. Kind of.
Yep. Yeah, it is very beautiful. It's one of those things, right? So late Miocene, I'll cruise along here. Now we start to see what Nevada looks like today, which is the Basin and Range province, right? It's bounded by the Sierras. On the other side over there, it's bounded by the Columbia Plateau. To the north, there's a little bit of Elko County that's in the Columbia Plateau, and in the south, actually some of the water drains into the Colorado drainage. But it starts to pull apart. And what I love about the place is there's 99 mountain ranges, and because the extension is east-west, all the mountain ranges strike north-south. They're not as big as the Sierras, but if you're anywhere in Nevada in the Basin and Range during the time when the sun is out, you know exactly which way is northeast, south, and west. Because you have the sun going across the hemisphere, right? And you know the mountains are northwest, so all you got to do is figure out, oh, okay, well that's way south, so that's north. And that's really helpful when you're out deer hunting or something like that. But they all strike north-south. So tectonically, here's kind of what this looks like today. Jim Falls loaned me this slide. So we have all of this movement along the San Andreas, because we've got this strike slip fault pushing this plate, right, this way, again, along the North American plate. And Nevada has a zone of that called the Walker Lane. And this is actually where most of those bonanza gold deposits are formed, just because of this here. 25% of the movement along the San Andreas is actually in Nevada. All these little faults that you see in here that are moving, because it's not one nice discrete spot. It's an entire continental plate sort of tearing along this direction through a bunch of little faults. Yep, Ridgecrest is way on there somewhere. So what has that done for us economically? Well, because our crust is only 20 kilometers thick, you know, it's much thinner than most of the craton of the continent, we have a lot of geothermal activity. And this is a little cartoon cross-section of what that looks like. Nevada actually is the #1 per capita producer, but behind California in terms of the actual generation of geothermal energy. But we have 27 different geothermal plants in 17 fields. And thank you for coming. Yeah. Did you get a hand lens?
Oh, I didn't.
You better get
I'll
one.
grab one, yeah. Sorry, I have a class at 1.
Yes. Yep, there you go.
Thank you so much.
Yep. So how does that work, the geothermal here? You have groundwater here that's coming in, recharging, because it's you know, typically not magmatic water that's coming up here. It's groundwater that's coming in, but it's being heated by this hot rock here, and those hot fluids then can be pierced by wells. Geothermal wells in Nevada are anywhere between 500 and 5,000 feet deep, somewhere in that. And they typically have line shaft pumps on them, so they're pumping hot water on them. I could get into the technology of that, but it's progressed through the 30 years geothermal's been around, to the point where that hot water comes up, it goes through a heat exchanger, and it heats a motive fluid. So you're not flashing, they're no longer flash plants where you take the pressure off and it forms steam and it drives a turbine. You're heating through a heat exchanger, something that boils at a lower temperature, like isopentane or RU-134, if you're familiar with that. Where do you find that? Exactly. That's the refrigerant in your air conditioner in your car. And that then drives a turbine and comes back, and the hot water is then re-injected back into the ground. So it's a non-consumptive use of water. You're really just pumping it up, re-injecting it back in here, and the reservoir engineering of geothermal, which is really fascinating, is unraveled in each one of these fields where they determine where are the hot rocks, because when I return my hot water I've removed the heat from, I need to put it back there, because the tracer tests that they have done on these things would indicate that from the time you pump it to the surface to the time it's re-injected and comes back at you can be as short as 9 days. So you really just have the earth as a boiler heating it, and you're recirculating the water, right? That's how it's evolved, and that's in 30 years, and that's pretty cool. Last year we had 3.5 million megawatt hours of electricity produced from these plants, which is enough to power 280,000 homes. And that's renewable energy, right? That's cool. So,
And that talk is on YouTube, by the way.
Is it?
The one you did, yeah.
Oh, okay, good. So here we are in the early Pleistocene, right? So now we're going to see all those lakes out there that were formed during those 4 ice ages, and some of the things that were, you know, associated with those, right? The sand dunes. But you can see all of these inland lakes that were formed during those ice ages that filled up. You can go see the relic shorelines of these. If you're on I-80 going east of Reno, all the way over here, you can, if you start looking, you can see the relic shorelines of the ice ages on the sides of many of the mountain ranges that are out there, because these aren't all that old, right? And those continued, and then they dried up and formed salt. Playas that are out there, some of the younger gypsum deposit formed then, but the one that's most significant and most interesting, I think, is this one. So here we are in Esmeralda County. This is called a salar deposit of how they actually form. And there's one of these that's being mined in Esmeralda County. It's the only lithium mine in the country. And this was the geologic model that was taken to southern to South America to find most of the salar deposits that are being pumped to produce lithium today down there. And in this basin, so you're landlocked, you're the basin and range, right? The water's not going anywhere. And you have these airfall tuffs and rhyolitic, lithic airfall tuffs and rhyolites typically have high lithium contents, because lithium's not an uncommon metal. You know, it's everywhere. In fact, it is really very highly concentrated in those basins out there in the playas, right, where Burning Man is at. And I've always thought to myself, and the westerly winds flow this way, so the playa is blowing high lithium dust into Burning Man.
That's probably why it's.
What's the pharmaceutical use for lithium? It's the primary component of Prozac, right? Makes everybody happy. That's why at Burning Man everybody's happy. They're breathing lithium dust. So, but in this case, you have this basin that had, I remember one company went in and they drilled a 3,000-foot core hole through the bottom of the basin to the bedrock. It was really interesting. They let me look at it, and there was halite layers in it and so forth, because there's a lot of chlorides. And those lithium ions concentrated, because they're soluble in chloride, into the bottom of the basin here. And when Foot Mineral, which was part of Newmont many years ago, went drilling for potash, they were drilling for potash deposits here. They realized, holy smokes, there's like 200-300 ppm of lithium in this water down here in this basin. And that resulted in the first lithium mine, I think, in the world at the time, because there wasn't a lot of uses for lithium 50, 60 years ago. Now we have pharmaceutical, we have greases, and of course the big one is batteries, because it's the lightest metal, right? The price of lithium has gone up fourfold. We've had 12,000 mining claims staked on brine and hard rock lithium in the state. We have 2 mines being permitted that are hard rock. They actually are a lithium-bearing montmorillonite called hectorite. It's about 3%. And there's one in Humboldt County being permitted at this point in time. It's a fairly complex flow sheet, but if it goes into production, it would produce about 10% of world lithium production. And they want to make the downstream products there. So,
Question for you.
what's that?
I have a question.
Yep.
So, at the seminar, Ioneer has the 100% mining rights.
Right.
But it's BLM land.
Right.
Do you think that they'll have a problem putting their operation
Nope.
going?
I don't think the permitting of those is going to be a difficult thing. The challenge is going to be coming up with the financing for it, because it's a first-time flow sheet, right? Nobody's done it before.
That's why they're 11 cents a share right now?
So, because they're gonna, I mean, it's like the one to the north. Ioneer's the one in Esmeralda County that has the lithium boron deposit. And then the one in the north is Lithium Americas. And they're actually in the NEPA process right now on federal land, going through the actual permitting. NEPA is the process by which, if you're on federal land, you have to go through a plan that shows from beginning to an end what this surface disturbance is going to look like, how you're going to mine it, how you're going to close it, because it's on federal land, it's on public land. Most everything in Nevada is. Nevada's 85% federal land. So I think, you know, if they can come up with a good argument and raise $500 million, they'll have a good chance. Because that's about what it's going to take to build one of those plants. It's not complex machinery. It's an sulfuric acid leach, much like copper dump leaching is. But it's just, it's new. It's a first time. You know, there's always risk associated with that, with the investors. So I hope they do. You know, because I would love to see us be the biggest lithium producer in the world. Because, you know, right now the lithium is all being produced as lithium carbonate, and you know, some of it is processed in the U.S., but a lot of it's going to China. You know, that's the game over there. Is let's get everything over here so we can do the end processing, and that's a risk that we have as a country, I think. So this is what the mine looks like here. This is the mine in Esmeralda County. It's operated by Albemarle, one of the 4 big lithium producers in the world. There's only 4 companies that produce lithium. And they actually have about 50 shallow groundwater wells here. When I say shallow, 600-700 feet, right? And they pierce these very low transmissivity aquifers. There's 4 of them. And they're mainly in old ash layers down there. So they pump, you know, probably a maximum of 100 gallons a minute out of each well. You can't pump the wells too hard. And they put that, bring that to the surface. That Apex lime plant sells them chemical lime, which they mix and add here, precipitate out the magnesium salts. And then they progress it through this racetrack of berms and lakes and so forth here over the course of 2 years, and it goes from 200 parts per million to 5,000 parts per million through evaporation. So their process uses the sun to evaporate, and then when it hits 5,000, they pump it into a plant, add sodium carbonate, and they precipitate out lithium carbonate. Pretty simple inorganic reactions. Lithium carbonate is the building block of most downstream lithium products. So from there, they make it to lithium hydroxide, which is what batteries use. I'm not sure what Prozac uses, some organic. And there's 75 people, who've been employed doing that for many, many years. So here's kind of summarizing here the mineral and the production values here. This graph has a whole bunch of spreadsheets behind it that we have to update every year. But you can really see the price of gold here, because this is gross value of production. So it's what's being paid for gold, silver, copper, zinc, geothermal energy, and barite, the major things that are produced. There, 2018, $8.4 billion. So what does that mean? What's California's biggest export?
Almonds.
Amethyst.
Enhancements.
No, it's airplane parts. I love this. I found this here a while back, and it kind of brings us into context. The biggest export from every state, right? It's airplane parts, right? But it just meant to show that in the scheme of things, that gold production, we're a net exporter of gold in this country. It's one of the few things that we have. We produce enough gold, almost enough copper, molybdenum, and a few things that we do not have to rely on inconsistent, dangerous parts of the world to do. Lithium is one of those ones that everybody worries about because a lot of it comes from South America, and the other thing that's required to make a lithium battery. You need three things to make a lithium battery: lithium, cobalt, and flake graphite, right? Most of world cobalt production comes from the undemocratic Republic of the Congo. And that's dangerous, right? We do have some cobalt, byproduct in the US, but it's one of the things in the critical mineral initiative that we're trying to work on with our allies, the Canadians and the Australians, all the countries that are stable democracies, to make sure that we don't get shut out and our industries have those materials to do the things that we need to produce. So my last few slides here, and Lucia and I put this together, by the way. This is one of Lucia's maps. It's the most recent one. It's a really cool map. Lucia has become the map maker for the governor's office of the state of Nevada on land use issues. And this one she put together actually shows land that the Navy wants to withdraw that's in conflict. These are geothermal plants here. This is a major part. The Navy wants all this for bombing ranges and so forth, and there's a lot of conflicts with that because it's the heart of our geothermal country. These are bighorn sheep sightings. There are all kinds of good layers that she's put together here. And with that, I can really say this: you really need to have a GIS class if you're going to be in this business. You almost need it for anything. Even I took a GIS class. It was like 12 years ago or so when I was working for Water Resources, but it's like I was such a dinosaur, I needed to do that. Because whether it's water, minerals, or anything, that's the tool, ArcGIS. Field geology, of course, got to have that. Hydrogeology was very valuable to me. I took that from a guy named Jerry Benke here years ago, and understanding that in water was, it's critical. I think for geologists, it's critical for a civil engineer, because water's a big part of the game there, knowing about drilling the well and doing those things. It even helped me when I was running leach operations, because that's just really hydrology, how fast are you leaching stuff through ore piles. Economic geology, which I'm so happy we have here, and I'm sorry Hannah couldn't make it. She and I were emailing each other, and I know her grandma died, otherwise she would be here. Environmental permitting and compliance, anything that has to do that. I don't know where that exists in the curriculum, but it's a part of the game anymore that you have to know. And report writing and oral presentations. That's always tough for geologists, right? And always tough for me, but in order, I mean, the geosciences, just like engineering, you know, you have to present complex topics that, and often have to present those to political science majors, right, and politicians. And there we go, and those, and you know, and you have to be able to be able to put it in a context where people can understand it. You know, because a lot of the decision makers on those are not geoscientists or engineers, and that's I found to be a challenge over my career, right? Yeah, an important part. So on the mining side, you know, there's all kinds of different disciplines that are part of the symphony to produce an ounce of gold or a pound of copper. Exploration geologists, mine geologists, environmental scientists, because those are the folks that do most of the permitting and compliance. I mean, all mines have permits, and they have to take water samples and air samples every month and so forth, and there's a role for that. And you know, I put this was a slide that one of our other people, Courtney Brelo, put together here in an education thing, and these are the mining schools in the U.S. You know, I could say that Chico's one of those because you have economic geology, but by definition that means that it has mining engineering, geological engineering, economic geology, and so forth. And if you're going to go down this path and you want to go pursue a graduate degree at some point, which I would not recommend that you do right out of school. I always recommend go work for a while and figure out what it is you want to be before you go to graduate school. And 2 of my daughters listened to me and 1 didn't. So, but they're all doing fine. I was supposed to show up with this today, but I didn't. So I have a sample for you that is down in Las Vegas, and they're going to cut it down at UNLV, but it was collected by Nick Dole and the MP Minerals mine geologists. It's a relatively rare high-grade piece of basins that came out of the Mountain Pass rare earth mine. Not flashy, right? But the rock is 40% rare earths. Here's a piece of basnasite here. Everybody thinks, oh, that looks like a granitic rock. Yes.
Is it 40% what, sorry?
Rare earth elements. And that deposit is the light rare earth. So it's, what are the light rare earths? Cesium, lanthanum, right. There's a hole in rare earths, so that big line, you know, down on the periodic table. And that deposit, which has been operating since, I think, the 60s, Howard?
Yeah.
Right? Because I learned about it from Howard.
And yeah, it's been down for a while. I mean,
It's back up and running.
Back up and running.
Yes, right.
Renovated their mill.
Yes. And you know, if you guys are ever down there, I'm sure they would give you a tour. Because I specifically asked for this rock, and they asked, what is it for? And I said, because I'm going to go give a talk at Chico. And they said, no problem. They don't hand out this stuff very often. So you guys can pick that up when you come to GSN next time. I should have it ready and cut by then. Okay. And references. And that's it. I'm sorry I ran over. You had such good questions. And I'm here to answer any other ones that you might want to ask if I can be of any help to you. Thanks for coming. I did bring a few things here, which I think maybe I'm going to give to your department head here, because they are addresses and names of the mines and entities that are operating in Nevada, which, you know, if you have an interest in doing an internship or something out there, there are companies that hire, you know, economic geologists and engineers in their, you know, usually junior year, you know, summer. And they provide you with a place to live out there because they know that that's a challenge and do that. The Division of Minerals actually hire 8 interns every year for our abandoned mineland program, and they're usually people in their sophomore or junior years, and they go out and they map old abandoned mineland work and fence them. It's physical work and it's camping, but I would entertain any applications that you have. There are people up there that we'll find you a place to live, and it is a good way of walking away with about 10 grand in the summer.
Richard,
Yes.
I'm the president of the Association of Geological and Environmental Science Students, and we'd like to give you a mug for coming.
And your name is?
Morelia. Hi.
Morelia, nice to meet you. Thank you so much for this.
Thanks.
Appreciate that.
One quick plug before everybody takes off. In the fall, if we get enough people, I'm teaching applied paleontology, and that's the one course we have that does cover CEQA and NEPA, environmental regulations, and how you do reporting and budgeting, all that kind of stuff. So that's the one place they can hear about.
That would be good. You know, I was going to mention too, and I wasn't quick enough to get this, but my certification as a registered geologist is through the American Institute of Professional Geologists, AIPG. And for states that don't have their own ASBOG test and so forth, that's usually what you do. AIPG is a international organization headquartered in Colorado, and it has a lot of student chapters. And you know, that might be something that this organization or this group might want to be a member of. You could have a student chapter, and you could have it as part of your associated geological and environmental, you know, the same group. And it would give you student membership into this thing, which gives a lot of resources that are available to you then online, and field trips, and webinars, classes, you know, that are generally free, and an annual convention that happens. And I think the next one actually is in Sacramento. It was in Vermont this year, and next year it's in Sacramento. But AIPG student chapter membership, I think, would be a good fit for this department, because it's not just mining, it's all geoscience related. So look it up, aipg.org, and I would be happy to be your signer for that. You need a certified geologist to be the sponsor, if there isn't one around. Yes?
I think student membership is free. I signed up when I went to GSA.
Did you?
Yeah.
Good.
IPG. Yeah.
Good.
So, just putting that out there.
Yep.
It's a good idea though for the student chapter.
Yeah, a student chapter would be great.
Yes, that's good.
There is one at UNR. There's a lot of different colleges have got one, so there's some good things to do in it. You know, Lucia's right. This person that I was mentioning, that she's in the midst of getting her certification as a certified professional geologist right now.
Lucia's an alumni.
Yep. Anything else? Vic, don't you have questions?
Yeah.
How did I do on the tectonics? I struggle with it, but you know.
If you go back to the.
Are you serious?
No.
He is, but don't do it.
But if you look at it, it almost looks like the relationship of a triple junction.
Oh. Here's a new geologic theory. I love that. Well, I mean, if you look at it as far as all of those accreted, where is it? Where is that slide?
This was a map that shows trend.
Yeah, right.
And notice that there may be failed arms in that trend, but the relationship of about 120 degrees makes me kind of suspicious.
Well, all those metals had to come from someplace underneath, right, and get leached out.
I mean, that's a stretching phenomenon.
Yep.
And so it allows fluids to move vertically.
We can argue about it at lunch.
Sorry to bring it up.
Anything else?
Thanks again, Rich.
Thank you.